So we are in, what are we in? Generalized linear models with examples in R. And we are in chapter 2, question 2.17. So here's the question. So for a sample of 64 grazing Merino castrated male sheep, I guess they're called wethers, the daily energy requirements and weight was recorded. And that's in the data set sheep, but they've also reproduced it in the book, and so I reproduced it here, the table. To read this table, notice that the weight column is spread out over several columns just because it's just a big, long 2-column data set. Okay. So here's the 4 questions. So we're supposed to fit a linear regression model to it, plot the data plus the systematic component and 95% intervals of the fitted values, interpret the model, and which assumptions appear to be violated, explain. So we'll just run through all of that without breaking it out into individual questions. It's simple enough. So first we need to get the data up and going. I've already done this here, so we need to install and load the GLM's data package if you haven't already on your local machine. If you're doing it in Colab, you need to install it every time. Okay. What data do we have? Well, we have the data set that is sheep, okay, and that's part of the GLM's data package. And then I'm just relabeling that data as sheep, and then we're just getting a look at it here. Okay. So there's the data right there. This is just the first 6 rows of it, but it has, many, many rows. Okay. I guess it doesn't matter. So I've already ran this, that's why all of that's there. But so the first thing that we're supposed to do is to fit a linear regression to everything where we're regressing energy on weight. Okay, and so that's what I've done here. And then we're going to go about plotting it. Okay, so we're going to plot the raw data, and then we want to plot the line that's implied by our linear regression, and that's what I'm doing with this line right here. Okay, and then it also asks us to plot the 95% confidence intervals around all of that. Okay, and so the plotting is actually done here. So I have some lines in a polygon that just makes a shaded region for it. Okay, right there. And in order to get those, I need to do the following. So so I need to define the domain of my data, the x values, the weight. Okay. So I define all the values of weight from the minimum that was seen in the data to the max. In practice, I could kind of extend, to either side of that, maybe a little bit. Okay, and then I just have some data points here. I just chose to use the length that was in the data, but you could use 100 or 50 or 10. It wouldn't really matter here. Okay, and then I'm going to make predictions on each value in weight seek. Right, so it is though I am running each value of weight here back through the implications of my model here to get my best guess of energy output. Okay, so that's what I do with this line here. Okay, and so this will just give me a matrix of fitted values plus their 95% confidence intervals. Okay, and then those prediction intervals go here, right? So I have the upper interval, the lower interval, and then I'm just shading in the region in between. Okay. And then I'll also look at the summary of the output here. So I've done all of that. Okay. So here's the summary of the output. Okay. And what it looks like is that energy is increasing with weight, okay, by about 0.04. What are they? Megacalories per day per kilogram in body weight. I guess that's a mega, I'm not sure. Okay, and it seems to be significant. So now let's look at the plot. So here we have the plot. So again, I have the raw data plotted as points. And then I have my regression line as this solid line in the middle. And then the 95% confidence intervals are represented by the dotted lines and then the shaded region. Okay, so so it kind of looks like probably one of the violations here is that it's kind of heterogeneous variance as I go across X. It might be a little bit hard to say. It could just be a sparsity of data, but but there might be some reason why there's less variance on smaller animals than larger animals. I can imagine that's the case. But anyway, I thought, well, one thing that we could do maybe to try to make it a little bit more homogeneous is to use a log transformation on energy, and we could try other transformations if we wanted, but I just did this one just to kind of go beyond what the question was asking. So I do the same thing, but everywhere I am taking log of energy. Okay, and so when I do that, I get a qualitatively similar result here, right? We're on the log scale now, and on the log scale, log energy goes up by about this amount for every increase in 1 kilogram increase in body weight. Okay, but here's our plot, and this seems, I think this is probably doing a better job of kind of creating better variance, more homogeneous variance. Okay, so in other words, when we're log energy, the variance seems to be more homogeneous. But okay, anyway, we'll call that good.